Yeah, let's get started. So today we're talking about more, it's going to be some graphing for a few more days. So I think we've got graphing today, graphing on Wednesday, graphing on Friday, graphing on the next Monday. It's kind of a graphing world we're living in until we get to trig. It's a lot of graphing. The thing about graphing is it's an important way to visualize what something looks like. Right? Like that's why we graph a lot of functions, is just so we can be like, oh, well, I know what the behavior of this thing is as we go this way or that way. That's, to me at least, that's the main idea of why we talk about graphs of functions, because it helps us kind of understand what they're all about. So let's look at a few more common types of functions to graph. So let's start with some exponential functions and then some logarithmic functions. Graphing logs and exponential functions. Yeah, this feels a little. Sorry, this is like feels not very secure. I'm gonna need to bring a screwdriver in here later and tighten that up a little bit, but we can worry about that later. So, exponential functions. We're looking at something like y equal to a to the x, where a is positive and greater than 1. So we don't deal with bases that are negative because they're problematic. We don't deal with bases that are 0 because they're problematic, or 1 because they're not very. So just as a quick kind of, I'm going to write a few things down here on a different piece of paper for one moment. So just so you all know, if you were looking at y equal to 1 to the x, it's not that it's not allowed, it's just that it's not very interesting. What's 1 to any power? 1. So this just becomes y equal to 1, which is a constant function, right? It's a horizontal line. So this doesn't really qualify as an exponential function. On the other hand, I also want to point out, if you had something like y equal to -9 to the x, that's problematic because it doesn't work most of the time. If you try, my favorite example is if my power was 1/2. What's -9 to the 1/2 power also known as? Ooh, that's the square root of -9, which isn't real. So these are a couple reasons why these are bases that we don't look at, because they just don't work very well. In fact, I should show you all just because I think it looks neat. And also because honestly, Desmos draws a better graph than I do. I'm not ashamed to admit it. I can get this over here. The thing's the wrong way. Sorry. I keep trying to go this, I move things this way to go over there, but oh wow, and now I'm really screwing everything up. Okay. But it keeps wanting to go the other way because someone changed the way it works. So, but let me just show you really quick here because I think it's cool. So we can graph some nice exponential function like 4 to the x. And it has the usual exponential shape, which we'll talk about in a minute. The things to note here, we've definitely got an intercept at 0, 1. It definitely gets way, way, way big if you go to the right, and it gets very, 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 very small, but still positive as you go to the left, right? My y values are very, very positive or very, very small. They don't ever really get to 0, right? That's just an approximation thing because they can't give you enough decimal places to show you what it's approximately equal to. But what I want to show you is if you try to graph something like -9 to the x. Now you might notice there's a bunch of little points there. Right, there's a bunch of points there, and you get some stuff here. Oops. But like, what's going on? Well, the thing that's happening here is this function is really only defined when you have nice integer inputs. Right? If you try to do -9 to the 1, great. You get -9. -9 squared, 81, and so on and so on. -9 to the negative first, 1 over -9, which is, it keeps wanting to go away. If I zoom in. Where'd you go? All my points went away. Sorry. I don't know what happened to them. Anyway, the point is that you only get a few things. It's not a very well-defined function. There's a lot of pieces that are missing. There's a lot of values of x that are not in the domain of this function. We typically like to limit ourselves to functions that have reasonably decent domains. So that's why we're not going to look at functions where where the base is negative. Okay, so back to this stuff here. I can brighten that up a little bit. So when I'm thinking about exponential functions, I am thinking about picking a few nice points to plug in. If I wanted to graph something like y equal to 3 to the x, for example, I'm going to pick a few convenient values of x just to plug in. So if I pick x equal to 1, 3 to the 1 is 3. If x is 2, 3 squared is 9. And if x is 0, what's 3 to the 0th power? Yeah, thank you. And if x is -1, you get 3 to the -1, which is 1/3. So if I try to plot these points, I'm thinking, okay, I get the point 0, 1. I get the point 1, 3. I get the point 2, 9, which is maybe way up here. I get -1, 1/3. I'm not trying to be super duper precise, but I am trying to get the right sort of look here. So there's maybe y equals 3 to the x. And it's got the usual hallmarks of an exponential function. It's growing very, very rapidly as you move further to the right. It's decreasing downward to the left, closer and closer and closer and closer to y being equal to 0. It's never going to get to 0, but it's going to get very, very close to it. So a few things to think about when we're graphing an exponential function. The first thing I always think about is the y-intercept. is 0, 1. And I should say, this is always going to be true if we haven't done any shifting, stretching, any sort of transforming. Right? If you've just got your basic exponential function, you're always going to need the y-intercept of 0, 1. And we're always going to get, or I should say we're not going to get, there's going to be no x-intercept. We never get down to the x-axis. We get very, very close to it, but we never actually get there. Bless you. We're also going to have a horizontal asymptote of the line y equal to 0, also known as the x-axis. All the horizontal asymptote is a value that the function gets closer and closer to as it either goes way out to the right or way out to the left. In this case, as you go further and further and further to the left, the function gets closer and closer and closer to a y value of 0. It never actually gets there in this particular case. And then lastly, maybe not lastly, there's no vertical asymptote. So as you move further and further to the right here, it kind of maybe looks like you might be able to say that there could be a no, we can't. I don't even want to say those words. I don't want to put them out, right? We don't get a vertical asymptote because the x values can keep getting bigger and bigger and bigger. There's no place where x isn't allowed to be plugged into the function. And that's usually where you find a vertical asymptote is where you can't, where you like get division by 0 or something like that. It's where we often get a vertical asymptote. Not happening there. X can be any value. There's nothing that's not in the domain. So we're good to go. Domain is everything. Okay, that's the thing I want to say is the domain is all real numbers, -infinity to infinity, and the range is all positive numbers, 0 exclusive to infinity. A couple other things here. The bigger your base, the steeper the graph. So if I instead were to try and graph, say like y equal to 4 to the x, it's going to have the same sort of shape, except well, I'm going to think about instead of plugging in 1 and getting 3, now if I plug in 1, I would get 4. If I plugged in -1, I would get a smaller value of 1/4. So it's actually going to be a steeper graph. Bless you. So there's maybe y equal to 4 to the x. But all of them have this same sort of shape where they're just going from the left, very, very small, and then you hit 0, 1, and then you take off. Yeah. The last thing I want to put on over here is that these exponential functions, if a is greater than 1, if your base is greater than 1, then the function is increasing. Meaning it's getting bigger and bigger and bigger as we go from left to right. And we'll see a little bit later on, another example, if your base is between 0 and 1, then the function is going to be decreasing, meaning getting smaller from left to right. Any questions about what I've said so far? When I think about something like 4 to the x or 3 to the x, I really just think of as x gets bigger, I'm just multiplying the base by itself more and more times, which is why the y values get bigger. Right? 4 to the third is 4 times 4 times 4. 4 to the fourth is 4 times 4 times 4. Right? As my x values get larger, my y values get larger. You could also think about the opposite thing happening if your base was like 1/2. Right? If you have 1/2 to a power, the more times you multiply 1/2 by itself, the results get smaller. 1/2 times 1/2 is 1/4. 1/2 times 1/2 times 1/2 is 1/8. So if we had a base that was between 0 and 1, our outputs would get smaller and smaller as the x values got larger, which we'll see on the next page here. But before we do that, let's graph the inverse function, log base b of x. I don't know why we didn't pick the same base when we were at this, but we didn't, so we got. So to graph a logarithmic function, we're going to do the same sort of thing. Now, what I really want you to see about this is for a logarithmic function, we literally interchange the role of x and y, which is what we would do, right? If I was trying to rewrite, in fact, let me grab this. If I was trying to rewrite y equal to 3 to the x as a logarithmic equation, that would become log base 3 of x equal to y. Usual, right? Usual relationship. And then if you're trying to find the inverse function, you switch x and y. So you get log base 3 of y equal to x. That seems, oh, you know what? I did it backwards. Sorry. I was too into it. This is what you would get first when you switch them, right? Log base 3 of, yeah, right? Yeah. Log, yeah, 3 to the x equals y. Yeah, 3 to the x equals y. And then you would switch x and y to get the actual inverse function. So those are the, sorry, I was like too caught up in it. So when we think about graphing something like y equal to log base 3 of x, I'm going to do the same sort of thing and just pick some convenient x and y values. And what we should notice here is they're going to exactly switch places from the previous one. Instead of picking x equal 2 and getting y equal to 9, now I'm going to pick x equal to 9, and log base 3 of 9 is 2. I'm going to pick x equal to 3, and log base 3 of 3 is 1. And x equal to 1, and log base 3 of 1 is 0. And x equal to 1/3, and log base 3 of 1/3 is -1. And we can keep picking smaller and smaller and smaller values of x that are still positive, and we'll get more and more negative values for y. Like if you pick 1/9, 3 to the -2 power is 1/9. So we can see that the smaller the x value gets, the more negative the y value gets. So if we pick some points, if we try to plot these points here, when x is 1, y is 0. When x is 3, y is 1. When x is 9, y is 2. Okay, fine. When x is 1/3, that's when it gets a little hard to graph here. I'm going to plot those points. So what we have is something that looks like this. You've got a vertical asymptote at the y-axis. Yeah, question. So that's a, you know what? That's a really good question. I don't know if I have an actual precise definition of the word asymptote, but what I would say is when you have an asymptote, so I haven't drawn either of them because they're both on an axis for these particular examples, but an asymptote is a line, or typically a line, that the function gets closer and closer and closer to as we approach something. So a horizontal asymptote, like here, is a line, the line y equals 0, that this function gets closer and closer to as you move way out to the left. On the other hand, this function here has a vertical asymptote at x equals 0, because as you get closer and closer to 0, the function gets closer and closer to this vertical line. So it's kind of like a border almost, right? Like you've got this line that's kind of like acting as a thing the function can't like cross over. Now, I hesitate to say that because we will see later on that you can totally cross the horizontal asymptote. So it's not fully like a hard border that you can't get across, but vertical asymptotes actually kind of are. So we've got this vertical asymptote here, and you just get kind of, as you get closer and closer to it, the function gets more and more negative or more and more positive. What I want to point out first and foremost about this logarithmic function is it totally looks like if we took this exponential function 3 to the x and flipped it over across the line, y equals x. So if we took this and flipped it across that line, y equals x, you would exactly get that, which is exactly what happens when you switch all the x and y values. You're literally just reflecting the thing across the line y equals x. It's kind of neat. The things I would think about if I was graphing a logarithmic function in general is the x-intercept is going to be 1, 0. You're going to get no y-intercept. You're going to get a vertical asymptote of x equal to 0, and you're going to get no horizontal asymptote. And what I would observe here is that all of, and this is true for inverse functions in general, all of the x and y things have interchanged places. Instead of getting a y-intercept of 0, 1, I have an x-intercept of 1, 0. Instead of getting a horizontal asymptote of y equals 0, I switched x and y and got a vertical asymptote of x equals 0. There's something else I was going to say too. Oh, domain and range also switch. Instead of the domain being all real numbers, here the range is all real numbers. Instead of the range being 0 to infinity, the domain is 0 to infinity. So I know we're really only talking about graphing these things, but I want you to see they really are inverse functions. They have everything interchanged, and that is the kind of big deal about inverse functions, is that all of the x and y things interchange roles. I'll probably say it a few more times. Lastly here, just like before, the base has the same restrictions. You can't have a base that's negative or 0, and you can't have a base that's 1. It's even harder. A base of 1 here is really complicated. Now, I will say, as I've said before, for logarithms, typically for a logarithm, our base is a nice integer number, like 2 or 3 or 4 or 10. Or what other number do we have for a base for logarithms? Not like a number, it's a letter number. E, right? That's the other usual base. Now, it's totally possible to have other strange bases like 1/2 or the square root of 2 or any other positive real number, but it is very typical to only see normal-ish integer numbers for your bases. And of course, E is the best. What else here? There's something else I meant to say here. Oh, no, I guess not. Oh, yeah. It's going to be increasing if your base is greater than 1, apologies, and it's going to be decreasing if your base is between 0 and 1, which again is kind of an atypical situation. You're usually not going to see a logarithm where your base is 1/3, but you could. And in sort of an opposite way, for exponential functions, if your base is larger, the function is steeper as you go further to the right. Whereas for logarithmic functions, if your base is larger, like say log base 4 of x, then instead of getting to the point 3, 1, like we got for log base 3 of x, we're going to get to the point 4, 1, which is going to be right there. And so it's going to look a little, there's not like a good, I feel like there's not a good opposite word for steep. Like, I guess it's a more gentle slope. It's not as steep. It's like more gradual race to infinity over there. Oh, sorry, that looks terrible. The problem is when you've got multiple of these, so you shouldn't be crossing the x-axis in your picture. I definitely encourage all of you to look at these graphs on Desmos because they look nice and appropriate. And you zoom in and out. And your drawing skills are not a factor. So, yeah. So these are your basic exponential logarithmic functions. And what I would say is the things to really kind of remember here is you're graphing an exponential function. You should have this shape, and it should go through the point 0, 1, and it should have a horizontal asymptote to the left most of the time. Similar for a logarithmic function with the usual kind of base that's greater than 1, you should have this shape. You should go through the point 1, 0, and it should have a vertical asymptote at x equals 0. Okay, now my hand is not the best for this, but it works okay. Everyone look at your right hand. If you're right-handed, which many of you are, look at your right hand. It's not really, yeah, let me zoom in here. Hopefully you can kind of see it. If you look at my right hand, you can kind of see, although not great, you can see a line kind of here and a line kind of here. This line looks like your usual exponential function, like 2 to the x or 3 to the x. So there's one we actually use. And this line down here, kind of where your thumb is, that looks a lot like the natural log of x, or log base 2 of x, or log base 3 of x. So if everything about exponential logarithmic functions, got your right hand. It's there. It's a good kind of, oh yeah, they're right there. I can look at them. So it's a good tip later on. I'm trying to remember what's what. just make sure if you're right-handed, which many of you are, that you don't look at your left hand when you're trying to do it because you're writing something with your right hand. Because your left hand has kind of the flip functions, which we'll talk about later. All right, where's my other papers? Always losing paper. So, for example, oh yeah, so now the other thing I want to say, which was 2 to the x versus 1/2 to the x. So if I was going to graph 2 to the x, really, let me just tell you, I'd probably, if I didn't care about being super precise, and I was going to graph y equal to 2 to the x, my graph would probably look like this. And I would say done, because that's all I really care about. I might point out, I might write down somewhere that the horizontal asymptote of y equal to 0. And if I'm just being asked to graph it, I kind of feel like that's enough. Now, I will say a lot of people don't. People are like, you could be a little. So if you really don't love only doing that, you could throw a few more points on there, like the point 1, 2, and the point -1, 1/2. But as far as I'm concerned, the point of graphing an exponential function is to get the shape right, and then to make sure you've got whatever intercepts you need, and to know where the horizontal asymptotes go. They're usually at 0 unless you've done some shifting one way or another. But since we want to see this with a little more precision in this particular example, we'll plot a few points. So I'm thinking always about plotting points that are easy, like x being 1, 2, or 3, and y being 2 to the first, or 2 to the second, or 2 to the third, and x being -1, -2, and -3, and give me things like, let's see, 2 to the -1 is 1/2, 2 to the -2 is 1/4, 2 to the -3 is 1/8. And of course, I didn't pick 0, but if x is 0, I'm going to get 1. I already knew that. So here are my nice points: 0, 1, 1, 2, 2, 4, 3, 8. I don't recommend plotting a bunch of points to the left just because you're going to get super close to the axis there and it's going to get messy. So I might just actually draw that one there and then pretend like the rest are there, because I'm just going to try and make it look like it gets very small over here. So then you just try and make it look smooth, which I'm doing a poor job of. And when you graph this, this arrow up here should be pointing mostly up, but still slightly to the right, right? You're still moving up and to the right, not just straight up. So I would try to draw it in that way. But that's kind of it. That is the exponential function, y equals 2 to the x. And it's got the usual things. It's got a y-intercept of 0, 1, and it's got a horizontal asymptote of y equal to 0. And that's kind of all that's really noteworthy about this function, other than its shape. Okay, but really we want to talk about this one because now we're going to look at its kind of twin over here, y equal to 1/2 to the x. And so let's actually just plot a few points as well for this one, because this is where we're going to see that when your base is between 0 and 1, it's going to change its behavior from increasing from left to right to decreasing from left to right. So if I pick some x values again, in fact, the same x values, let's see what happens. So if x is 1, 1/2 to the 1 is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. And if I pick -1, 1/2 to the -1, what's 1/2 to the -1? I think it's 2, right? Because I'm just doing the reciprocal of 1/2, which is 2. And 1/2 to the -2 is going to be the same as 2 to the +2, which is 4. And 1/2 to the -3 is 8. So what's happened here is all my x values have kind of changed, right? They've reversed themselves, and all the y values have stayed the same, or they've gone with the reversals, whatever you want to say. Really, what we have here is a reflection across the y-axis. Let's take a look. I've got the point 0, 1 still. I've got the point -1, 2, -2, 4, -3, 8. And then to the right, I've got the point 1, 1/2, and 2, 1/4, and 3, 1/8. And then we'll try to draw this not terribly here. That looks all right. So here's your graph of 1/2 to the x. It's still got a y-intercept of 0, 1. It's still got a horizontal asymptote of y equal to 0. the only other noteworthy difference here is one of them is increasing, one of them is decreasing. I should point out, this really does look like, in fact, it really is what you would get if you did the horizontal reflection. So remember when we talked about reflections a few days ago? Oh, wow. You get a horizontal reflection if you do a negative on the inside. You get a vertical reflection if you do a negative on the outside. So if I do a negative on the inside of this function, if I write, like y equal to 2 to the negative x, that really is the same as 1 over 2 to the x, which really is the same as 1/2 to the x. So 1/2 to the x literally is the reflection of 2 to the x in the y-axis. It's cool. And that's always going to be the case when your base is between 0 and 1, because as x gets larger and larger, you're going to be multiplying this thing by a number smaller than 1 repeatedly. So 1/2 to the third is 1/2 times 1/2 times 1/2, just getting small. You do it again, you get smaller. You do it again, right? Every time you multiply by a larger power, you're getting smaller and smaller and smaller and smaller. So that's why as we go to the right, where x is bigger, the y value is smaller and smaller. Let's see, what else to say here? So those are your kind of basic exponential logarithmic functions. And now what we're going to do with them is shift them around. Question? Distraction. Okay. So we're going to take all the, we're going to take most of the things we did the last few days, like reflections, shifts, probably not any stretches, because I know what this is about stretching. And we're going to see what happens. We're just going to move these things around and see what happens. So here's what I would say, and here are kind of the general rules for drawing your exponential or logarithmic functions. Draw your base graph or think about what it looks like. Flip, stretch, shift as you will, and then find the intercepts if there are any. So let's look at this first example of 4 to the x plus 1 minus 5. So I see a horizontal, well, in fact, I should follow my own directions here. Okay. So here's my base graph of y equals 4 to the x. To start with, y equals 4 to the x. Again, I don't usually think you have to do all of these things graphically, but it's good for me to show you what I mean. So here's y equals 4 to the x approximately. And now I have to look from the inside out. So the first thing that's happening is I've got 4 to the x plus 1. So y equal to 4 to the x plus 1 is going to shift me horizontally. And I don't remember, is it left or right? Going to be left, right? The horizontal ones, maybe I always like to think of it as kind of counterintuitive, because you might think adding 1 would make you go to the right, but it's actually the x needs to be 1 less to counteract it. You can also, and here's what I really recommend, you can think about, well, if I'm graphing 4 to the x, I know I'm plugging in x equals 0 and getting y equals 1. If I'm graphing 4 to the x plus 1, if I want to still get a y value of 1, what x value do I need to plug in? Well, I need the exponent to be 0, so x needs to be -1. -1 plus 1 is 0, and then 4 to the 0 gives me back to 1. So I'm thinking now, instead of getting 0, 1, I'm getting -1, 1. So shifting to the left. Instead of getting the point 1, 4, I'm getting the point 0, 4. So it's kind of looking like this. So there's my shift of 1 to the left. And then the -5 is going to bring everything down by 5. So this point of -1, 1 is going to go down by 5 to -1, -4. And this point of 0, 4 is going to go down by 5 to 0, 1. Now, the real important question here is, what's my new horizontal asymptote? Here, for the black graph, the horizontal asymptote was y equals 0. And for the red graph, when we shifted 1 to the left, the horizontal asymptote was still y equals 0. Because shifting 1 to the left doesn't change the fact that it's going to get closer and closer to 0. So you go way up that way. But now we're moving the whole thing down by 5, which means specifically the horizontal asymptote is going to move down by 5. So our new horizontal asymptote, or y equal to 4 to the x plus 1 minus 5, the horizontal asymptote is going to be y equal to -5. And now that we have a horizontal asymptote that isn't one of the axes, we typically draw it. And usually you draw a horizontal asymptote as a dashed line. So y equals -5, which is a horizontal line. I'm going to draw the dashed horizontal asymptote. It's not actually part of your graph, just like the center of a circle isn't actually part of the graph of a circle, but it's an important feature that we still want to make note of. And then we do our best to draw it. So we're going to draw it. It's going to look kind of like this. Oh, there's going to be an x-intercept. It would probably cross that other graph that was its original parent graph, but that's okay. It doesn't matter. So let's see. We drew the base graph. We shifted it both left and down. We found the y. Oh, we didn't find. Well, we did find the y-intercept. But let's talk about the y-intercept. So the y-intercept would be, of course, if you set x equal to 0, you're going to get y equal to 4 to the 0 plus 1 minus 5, which is just 4 minus 5, which is -1. On the other hand, the x-intercept is why we've talked about logarithms already. So if I wanted to find the x-intercept, I would be setting y equal to 0. If I set y equal to 0, I'm going to get, let's see, 0 equal to 4 to the x plus 1 minus 5. Well, we can solve this for x. It's not going to be very pretty, but that's okay. So we're going to get 5 equal to 4 to the x plus 1. And you could really use any logarithm you want here. You can either use log base 10 or natural log, or you could even use log base 4. I would probably default to natural log because that's my usual choice. But if you want to use a different log base, that's totally fine. I'm going to rewrite this as the natural log of 5 equal to the natural log of 4 to the x plus 1. I'm going to bring down the x plus 1. I'm going to run out of room. So that natural log of 5 equals x plus 1 times the natural log of 4. And then, okay, it's getting a little, I'm going to divide natural log of 5 divided by natural log of 4 equals x plus 1. And finally, x equals the natural log of 5 over the natural log of 4 minus 1. Sorry for having to squeeze that in there so much. So there's your not very nice looking x-intercept. Natural log of 5 over natural log of 4 minus 1. But there is an x-intercept and we should find it. Sometimes they're a lot nicer. So our x-intercept here is, yeah, natural log of 5 over natural log of 4 minus 1, comma 0. Sometimes, as we'll see in future examples, the bases will work out in a much nicer way. So just for instance, if this had been, instead of a 5, like an 8, we would have had a much better chance of making this look nice. So typically, this is all we really do with graphing logarithms and exponentials is we take your usual exponential graph that has the, the typical shape, and we talk about how it shifts, and then we find any potentially important points. Let's look at another example where things are maybe a little less terrible. Yeah. So look at this next one. We've got the graph of 2e to the negative t minus 2. Actually, I'm going to take a quick, I got time. I'm just going to say there are 2 other exponential and logarithmic graphs that I should mention just because they're kind of the ones that come up the most, which are the following 2. We'll come back to that page in just a second. You might use the back. So 2 important graphs. Specifically, f of x equal to e to the x. Kind of our favorite exponential graph. It looks like all the rest. There's nothing really that special about it. Okay, that's a total lie. It's very special. But at this point, it's just got the usual kind of stuff. Got an intercept at 0, 1, got a horizontal asymptote at y equals 0, and it's got the usual shape. In fact, when I talk about my right hand, looking at whether I've got an exponential or a logarithmic, I think of the exponential function as e to the x, and similarly, the logarithmic function is the natural log of x. So there's your graph of e to the x, and here's our graph of the natural log of x, or log base e of x, if you prefer. And again, it's just going to have the usual shape. This has a vertical asymptote. These are the two most important versions of your graphs, right? If you're thinking of any exponential function, the one you should think of first is e to the x. If you're thinking of any logarithmic function, the one you should think of first is the natural log of x. They're definitely the ones you're going to see the most as you move forward with mathematics, 100%. Yeah. And they're right there. Especially if you're young, you don't have a million lines on your hand like I do. They're really right there. They're kind of hard to see on my hand because I've got lots of other lines, but they're still there. I should draw them. No, I should not draw them on my hand next time I teach this. It'd be a bad choice. Or if I do, I should use some very, very easily wash-offable ink. All right, so here we have 2e to the negative t minus 2. So I see three transformations here. I see a negative power, meaning it's going to be a horizontal flip. I see a multiplication by 2, which I'm not thrilled about, which means it's going to be a vertical stretch by a factor of 2. Not my favorite. And then finally, I see a minus 2, which is going to shift this down to. So we see a horizontal flip, or reflection, I guess, is the mathier word, but flip is fine. And we see a vertical stretch. And then finally, we see a shift of down by 2. And of all the things here, well, I guess the flip and the stretch are both important, or the flip and the shift. So the flip is going to mean instead of going up from left to right, we're going to be going down from left to right. So here's I'm going to draw the things over here to make it kind of less cluttered on the final graph. So here's our original y equals e to the t. And here's our flip. Y equals e to the negative t. And then the stretch, I'm not going to worry that much about. I could draw it. I guess I'll draw it. I'll tell you what I'm really getting at. There's our stretch. So specifically, the y values are going to be twice as big as they were. So this 0, 1 point is going to become the point 0, 2. So everything's getting doubled up. But I feel like I'm not great at drawing the stretches. So here's my stretch. Now I'm hitting that. It's y equals 2e to the negative 2t. And then I'm going to shift down by 2. So our new horizontal asymptote is going to be here. And my graph is going to look something like this. Now I'm going to draw it purposely not exactly right, because I want to point out that if I hadn't done the stretching and thought about where things were going to be, I wouldn't exactly know where my intercepts were going to be. So I'm going to draw it like this, and then I'm going to talk about what we should do. So great, we've got this graph. We know approximately what it looks like. Before I actually go and graph it, let's find the intercepts. So I know that my horizontal asymptote is going to be, I know that's not an intercept. My horizontal asymptote is y equal to negative 2. By the way, for these graphs, your asymptote is just how much shift you've got. So if you shifted down by 2, your new horizontal asymptote is negative 2. If you shifted up by 3, your new horizontal asymptote is going to be up by positive 3. Same deal, similar deal for logarithms. So then I'm going to find, I would always start with finding the, I said with the y-intercept. So I should say for exponential graphs, they will always have a y-intercept because you can always set x equal to 0. For logarithmic graphs, you don't always get a y-intercept. In fact, you don't usually get a y-intercept unless you shift it to the left, but you always get an x-intercept. So I would always start with the thing you're for sure going to have. So to find the y-intercept here, I'm going to set x equal to 0. I set t, I should say t equal to 0 because we're using t, not y for x. Set t equal to 0, and you're going to get y equal to 2e to the 0 minus 2. E to the 0 is 1, and 2 times 1 is 2 minus 2, which is 0. So it happens to be here that our y-intercept is the same as our x-intercept, or our t-intercept. right? We're getting the origin as our point where we're crossing. So that's why I would say you just want to kind of think about the shape. I see that my shape looks like this. I shifted it down 2. I should draw my horizontal asymptote. And then I'm really just going to wing it. I don't really want you to plot more points. I don't want to plot more points. I know what the general shape looks like. If you really, really, really wanted to, you can say, okay, James, I really need to plot one more point. I could plug in t equal to -1, and we can get an approximation. So if t was -1, I would get 2 times e to the 1, or -1, minus 2. Okay. I know we've talked about e a little bit. E is approximately how much? Yeah, 2.7. So if I do 2 times 2.7, that's like 5.4. 5.4 minus 2 is like 3.4. So we could, if we wanted to get one more point just to make our graph look slightly nicer, you can go ahead and get one more point. I don't feel like it helps me. I feel like it makes my graph look worse, to be perfectly honest, because then I'm actually having to try and make it look right. And I've got that point up there, and it's going to be ugh. Okay, really 5.4? I feel like I didn't do that right. 3 point. I said 3.4. I forgot to start. It's okay. Sorry. Let's go see. That's another reason why I maybe don't do it. But there's my point there. Okay, it's gonna not look too terrible, I guess. I mean, I'm drawing it, so we'll see. I mean, it's not perfect. It doesn't have to be perfect. I really just want you to get the general shape right, knowing that it's right. And these exponential ones all do this thing where you just zoom way off either that way or way off that way. And then make sure you got the intercepts. In this case, there was only one intercept, the origin. Great. So our intercept is the 0.00. Okay. Yeah. So exponential functions, general shape, do the shifts, kind of it. Logarithmic function, same kind of deal. Start with the general shape, do any shifts or stretches or reflections, and then try to do the results. So looking at this logarithmic graph, I see a shift to the left by 4 and a shift down by 2. So when I'm thinking about something, especially like this with just shifts, well, I know that we're going to go left by 4, meaning my new vertical asymptote is going to move forward to the left. Right? It would have been x equals 0, but that's going to mean that my new vertical asymptote is going to be x equal to -4. Which you might as well get right there. And if I were graphing the graph that was just shifted forward to the left, my x-intercept would also have shifted forward to the left. Meaning instead of having 1, 0 as my x-intercept, my new x-intercept would have been -3, 0. But then we're also going to shift down 2. So that essentially I'm thinking of this point 1, 0 that would have been on my original graph going 4 to the left and 2 down. You don't have to have that point, but we certainly can. So really, I've shifted left and down, and now I'm just thinking of the usual shape. And if I didn't have all these stupid marks in my way, I would just draw it and then fill in the blanks. Meaning what I would really like to do is say, wow, I'd like some blank paper. I would really like to say, here's my graph. Here's my vertical asymptote, label it. Here's my logarithmic function. I've probably drawn it poorly, so I could maybe see it. And then find this intercept, label them. Good. As long as it looks not super crazy wrong, like as long as it looks like the logarithmic graph, even if the shape isn't perfect, as long as you've got the general kind of right idea, I don't care if the values are perfect or correct. I mean, I care that they're correct. So I would go, well, in fact, let's go and do it. So finding my, I'm definitely always going to have an x-intercept for a logarithmic function. We also will have a y-intercept here because we shifted to the left. But I still think it's a good idea to find the guaranteed thing first. Sorry, I keep getting out of frame here. So if I wanted to find my x-intercept, I'm going to set y equal to 0. So setting y equal to 0, we're going to have 0 equal to log base 2 of x plus 4 minus 2. And you can probably suss this out whatever way you want. I'm going to do the usual thing, which is add 2 over here. So 2 equals log base 2 of x plus 4. And then rewrite it as an exponential equation. So base 2 raised to the second power equals x plus 4. Really? 0, 0 again? Who thought about this? Not me. So then, that's not true. 4 equals x plus 4. So 4 minus 4 equals x. So x equals 0. And I guess if we had plugged in 0 for x, we also would have seen that we got y equals 0 as our y-intercept. If x is 0, log base 2 of 4 is 2, and 2 minus 2 is 0. How unoriginal. So there's our logarithm graph. And since I have a minute or two here, yeah, I got a minute or two here. I don't have any extra paper. What a poor planner. I would really like to give you one more example. We're not just so lovely. So, yeah. Let's do one more. Let's say we wanted to graph f of x equal to log base 4 of x plus 3 minus 8. That should be not too terrible, maybe. Yeah, that should be fine. Okay. So first we're going 3 to the left, which means we know that our new vertical asymptote is going to be 3 to the left. Instead of x equals 0, it's x equals 0 minus 3. In fact, you can always find a new asymptote just by adding or subtracting the number of the shift to your original 0. But there you go. And then we're going to go down 8. So let's see here. 1, 2, 3 to the left. There's my new vertical asymptote. And I guess I shot myself in the foot by drawing all the hash marks. Oh, well, life. So then let's find our intercepts because we know what the shape is. And we know it's going to be just something like this. So I'm going to find how I picked 3. I knew I was doing something dumb. Oh, well, I did something dumb. I guess I'll have to live with it. So if I pick x equal to 0 to get my y-intercept, we're going to get y equal to log base 4 of 0 plus 3 minus 8. Disappointing. Log base 4 of 3? I don't know what that is. I could use a calculator. I could also make a pretty good guess, though. Because I know that log base 4 of 4 is 1. The log base 4 of 3 is going to be a little bit less than that. I don't know how much exactly, but it's going to be a little bit less than 1. So I've got a number a little bit less than 1 minus 8. So I've got a number that's a little bit less than, or a little bit, yeah, less than 7. Negative 7, sorry. 1 minus 8 is negative 7. A little bit less than 1 minus 8 is a little less than 7. So less than negative 7. That's a very low y-intercept. Okay. How low can we go? So here's my y-intercept, maybe right about here. And then my x-intercept. So we're going to set y equal to 0. Oh man, I got my numbers backwards. Oh well. So this is going to be a dumb graph. That's all right. But let's look at our y. Okay, this is okay. This is what happens when you make stuff up. Sometimes you don't get the numbers right. If we do our y-intercept here, if we set y equal to we set y equals 0 to our x-intercept, 0 equals log base 4 of x plus 3 minus 8. So 8 equals log base 4 of x plus 3. So 4 to the 8th power is equal to x plus 3. So x equals 4 to the 8th power minus 3. 4 to the 8th is pretty big, like on the order of 20,000 maybe. So this graph is very, very, right? I mean, but it's still a logarithmic graph, right? It's still got the usual shape. So even if you had something stupid like this, the idea is still find the y-intercept, find the x-intercept if there is a y-intercept. find the vertical asymptote, and then draw the usual kind of shape, even if someone picks dumb numbers because they forgot thinking. All right,